Welcome, I'm Professor Sever. Today we're going to discuss limits from the standpoint of review in Calculus 1. So the squeeze theorem is an important theorem for us. We use it to prove a lot of theorems, but we also use it to evaluate certain problems that we couldn't evaluate another way, or certainly not another way easily. Let's look at this one. So now I have a complex function. All right, let's look at this. So this piece right here, the limit's undefined. The numerator is going to 2. The denominator is going to 0. So this quotient is undefined as x goes to 0. That quotient doesn't exist. The limit doesn't exist there. So you have the sign. So this quotient is not existing, and you have the sign of that times 0. Okay, so this is kind of a 0 times it does not exist form. So, and I'm telling you what the answer is here, so let's show that. Not by looking at a graph, which is easy to do. We want to prove this analytically. So we use the squeeze theorem. So let's look at the function here, and I'm actually going to show you how I come up with the upper and lower functional bounds. So remember what the squeeze theorem says. It says if you have an f that you're working on, you have an h of x below, a g of x above, and if those limits are 0. If the limit of this function is the limit of this function as x goes to 0, then the limit of the original function has to be the same. It gets squeezed in between those two limiting values. So how do I produce these two functions? Well, let's look at the absolute value of the original function. The absolute value of the product is the product of the absolute values. That's an easy algebraic result. Now, we know from trigonometry that the sign does not exceed 1, nor does it get below -1. Therefore, the absolute value of the sign of any expression never exceeds 1. So this is now less than or equal to absolute value of x times 1. Now let's remove, and this is what I'm looking at, remove the absolute value. So now this says the original function, when you remove the absolute value, it's less than or equal to this, but also bigger than or equal to the negative of this. So now I have a function above, I have a function below, which have the same limit of 0. Therefore, this limit is 0 by the squeeze theorem. This limit gets squeezed between 0 and 0, or pinched. Another example, and again, these trigonometric examples, a lot of times they work the same way. Take the absolute value of the function, y. It gives me a natural move where I'll look at the product of a bound for this function. The absolute value of the cosine of this quantity is less than or equal to 1. So now you take the absolute values off. The original function is less than or equal to this, and then bigger than or equal to the minus of the same thing. So where do these two functions go as x goes to 1? They both go to 0. Therefore, this limit is 0 by the squeeze theorem. So here's another example. So this one's a little more theoretical. I want to find the limit as x goes to 1 of f of x. Now suppose I tell you that f is bounded by this function on the left. That means f is bigger than this on this interval, and f of x is below this function on the same interval, except perhaps at x equal 1. So let's look at the limits of these two functions. If the limits of these two functions are equal, we're done. So we know the limit as x goes to 1 of sine of x minus 1 over x minus 1. Now technically we need to do a change of variables here, so let's let t equal x minus 1. And let's recompute the new limit in terms of the new variable t. So as x goes to 1, where does t go? Well, what's 1 minus 1? That's 0. Okay, so now I rewrite. T is going to 0. X minus 1 is t, so we get sine t over t. This is our favored trigonometric limit. We know this is 1. Okay, now that was a little tricky with the change of variables. Okay, so now this is simply a polynomial. How do you evaluate the limit of a polynomial? By functional evaluation, so you just plug in. So 1 minus 1 is 0. 0 squared is 0. 0 plus 1 is 1. Are these the same results? Yes. So we know this function goes to 1, this function goes to 1, but the function at hand that we're investigating, that's trapped between them on the interval. Therefore, it has to go to 1 by the squeeze theorem. So this was a more abstract example than the prior two. Let's look at basic continuity. So what is our equivalent? So let's state 3 statements that are needed to show f is continuous at 3. What 3 things have to happen? First, f needs to be defined at c. That means c needs to be in the domain of f. Second, the limit as x goes to c of f of x has to exist. That means, let's say it has to be L. So c needs to be in the domain. The limit as x goes to c has to exist. Let's call it L. Then this value L, which is the limiting value, that's the value of the limit, must equal the functional value. If all 3 of these things hold, we say f is continuous at c. So let's use this to show this rational function is continuous at c. Well, we want to investigate the limit. First, is 3 in the domain? Yes, because the denominator is not 0. Check. 3 is in the domain. Let's look at the limit. How do we evaluate the limit? We evaluate it by plugging in. That's actually going to give us this here immediately, but let's wait. So we evaluate by plugging in. So we get 4/5, and of course, what is h of 3? That is 4/5. Are these equal? Yes. Is the limiting value equal to the functional value? Yes. Therefore, h is continuous at 3. So also, let's look at this other rational function. Now let's state the discontinuities. Well, where is the function discontinuous? A rational function is discontinuous certainly at those values that are not in the domain. Which 2 values are not in the domain? 1 and -1. So those are the only 2 discontinuities. By this other example, we know if a value is in the domain, such as 2, the function would be continuous there. That's what our prior work shows us. All right, finally, we identify the vertical asymptotes. How do we do that? We have to evaluate the limits. We have to show that these limits don't exist for a rational function. So we investigate the limit work, which we see here. The limit at 1 doesn't exist, nor does the limit at -1, and that's enough for a rational function to state that they're vertical asymptotes. Now, if it's not rational, we have to do further analysis. So the next part of this same problem, so we have another rational function. We want to state the discontinuities. This time, the function's a little different, but has the same denominator as the last function. So, same thing, we set the denominator equal to 0. We solve, we get x equal 1 or x equal -1. Now that says the function's discontinuous there. Now, on the next step, we have to classify those discontinuities. We only have 2 discontinuities, 1 and -1. We want to determine if they're removable or they're non-removable. Now please take note, the determination whether a discontinuity is removable or non-removable is made by evaluating the limit. If the limit exists, then it's removable. If the limit does not exist, it's non-removable. So this one's clearly non-removable. The denominator goes to 0, the numerator does not. Therefore, this limit doesn't exist. Therefore, 1 is a non-removable discontinuity. Again, you must show the limit work here to make that determination. It would not be appropriate to go to graphing software, look at the graph, and say, I see a vertical asymptote at 1, therefore I know it's a non-removable discontinuity. That would be true, but you will most likely in your course, and in my course, you will be asked to show this work analytically, which means evaluate the limit. Let's look at the work on the next part. Is -1 removable? Let's see. So we evaluate the limit. We have 0 in the denominator, 0 in the numerator. That means we have more work to do. We'll factor the denominator, cancel. This equality is justified by functions that agree at all but one point. So now I have a rational function that I can evaluate by functional evaluation, plugging in, namely, so the limit existed. So we ask ourselves, did the limit exist? Yes. Therefore, this is a removable discontinuity. So we only have 1 removable discontinuity and 1 non-removable discontinuity. Finally, we identify any vertical asymptotes. We know that the non-removable discontinuities of any rational function are precisely the vertical asymptotes. And again, if this were not a rational function, we'd have to do further analysis. So we have a trigonometric function. Let's state the discontinuities of this function. We set the denominator equal to 0 and solve. So we see the discontinuities are -4, 0, and 4. So again, to classify those discontinuities, we have to evaluate the limit. That means we have to evaluate 3 limits. One at 0, one limit at 4, and another limit at -4. I have the work here, and so we can easily see that the first case, the denominator is 0, the numerator is not. That's obviously does not exist. Therefore, 4 is a non-removable discontinuity of the function. We have the same result at -4. The limit does not exist for the same reasons. Therefore, we have a non-removable discontinuity at -4. Now for 0, we have 0 on the numerator, 0 in the denominator. So we factor out in x. We separate the function. We get 1 minus cosine x over x times the other piece. And this piece goes to 0. That's one of our favored limits. And what happens in this piece? Well, functional evaluation. This is a rational function. This limit can be evaluated by plugging in, which is -1 over 32. So 0 times -1 over 32 is 0. So x equals 0 must be removable, and 4 and -4 are non-removable. And for this function, what are the vertical asymptotes? They're at 4 and -4 because these are non-removable discontinuities of this function. I'm not saying that every non-removable discontinuity of a function is a vertical asymptote, but here, as the denominator goes to 0, the numerator does not. What that says that this function on either side is getting extremely large, going to plus infinity, or extremely small, going to minus infinity. That's enough to say it's a vertical asymptote. I'm Professor Sever. Thank you for watching a review of limits.